You can predict the type of structure adopted by an ionic compound using radius ratios. In this screencast, you'll look at the logic behind this idea, then calculate the limiting radius ratio for octahedral coordination. The radius ratio is defined as the radius of the cation divided by the radius of the anion. In the ionic model of bonding, you assume that the ions are charged, fixed-size hard spheres. Cations are in contact with anions, so the distance between the centres of the neighbouring ions is equal to the cationic radius R+, added to the anionic radius R-. The most stable structure is the one that maximises the number of cation-anion contacts, since these are attractive. As a consequence, a compound will adopt the structure with a maximum coordination number subject to the cations and anions being in contact with each other. This means that a coordination number of 6, as seen for octahedral geometry, might be expected to be more stable than a coordination number of 4, as seen for tetrahedral geometry. In these figures, the ions are shown smaller than they actually are, so that you can see what's going on. For a particular coordination type, you can use geometry to work out the smallest possible value of the radius ratio for the cations and anions to be in contact. If the radius ratio is any smaller, the cation-anion contact is lost, which means this structure isn't stable. The smallest value of the radius ratio is called the limiting radius ratio. We're going to look at the sodium chloride structure, which involves octahedral coordination around the sodium ion. Showing the ions in contact, we can't even see the cation. It's hidden from sight behind the large anions. Taking a slice through the octahedral geometry, there are 4 anions within the same plane as the cation, plus 1 above and 1 below. For clarity, we'll leave those out of the figure. It doesn't affect the calculation, but it does let us see the cation. If the cation were any smaller than shown, the cations and anions wouldn't be in contact, whereas the anions would, so the structure wouldn't be stable. This means that the radius ratio shown is equal to the limiting radius ratio for this coordination. We can draw a triangle on the figure with the lengths of 2 sides and the angles known. We can then use trigonometry to work out a value for the limiting radius ratio. The calculation actually becomes simpler if we halve the size of the triangle, as shown. The sine of an angle in a right-angled triangle is defined as the length of the opposite side divided by the length of the hypotenuse. The sine rule states that for any triangle with sides of lengths A, B and C and angles of A, B and C, length A divided by sine A is equal to length B divided by sine B is equal to length C divided by sine C. Applying the sine rule to our triangle gives an equation relating the sum of the 2 radii to the anionic radii. The equation can be simplified as sine 90 is equal to 1. Rearrange the equation by subtracting the anionic radius from each side, factorising, and then dividing each side by the anionic radius to give the radius ratio. Putting in the value for sine 45 degrees gives you the limiting radius ratio, which is equal to 0.414.